Hello and welcome to another one of Dee's ADD videos. Today we're going to be discussing Newton's first law, an example with no friction. Excuse me. Alright, we're going to consider this pulley system that's completely frictionless. The surface here doesn't have any friction, neither does the pulley. The ropes have no mass or negligible mass. And the first question is, what must the second mass here be in order to achieve a constant velocity? Okay, in order for the system, in other words, to be in equilibrium. We know that this mass right here is 50 kilograms. Alright? So, what is the first step? The first step must be to draw the free body diagram. To do the sum of the forces in the x and the sum of the forces in the y, and do this for both objects. And then 3, just start solving for your missing pieces. Alright, so let's see it in action. So M1, what do we have going on with M1? Well, if I align the motion with the axis, so let me make it a slightly thicker line so you can see it in a different color. There's the positive x-axis. There's the negative x-axis. That would be the positive y-axis, and there's the negative y-axis. So, for mass 1, the free body diagram should look something like this. We're going to have the tension. I forgot to make my line thinner. It's fine. And then we're going to have, I'll label them in a second after I'm done drawing them. The normal force going straight up. And then we have the weight going straight down. Alright, these are the forces. Let me resize my pencil. So this was the tension, and that was in the positive x direction. This was the normal force. Little vector hats, and then this was the weight. Right? Now, if you remember, I told you whenever you have an angle of inclination, it's always the same as the angle between the weight vector and the negative y-axis. So there's your M1 free body diagram. Now let's look at M2. M2 is pretty straightforward. There are only two forces really acting on it. There's the tension pulling it up, and then there's the weight pulling down. And this is weight and 1 because they're two different objects, right? Okay, so there's step 1. We did the free body diagrams. Now what do we do? Well, we got to do the sum of the forces. So let's start with the sum of the forces in the x for the first object. So in the x, there's only two real forces. There's going to be the tension minus, here there's going to be an x component, which I'll draw in orange, to the weight, which would be going that way. Okay. But for object 1, those are the only two forces that are available to us. And I said constant velocity in the problem, right? So it should be equal to 0. And then the sum of the forces of the y direction for object 1 would be the normal force, which is in positive y, and then minus the y component there. Of the weight. That again will also equal 0. Alright. The second object's pretty easy for the x because there is no x motion, right? And no x pulling. It's purely in the y direction, up and down, whichever way, whichever one wins. Is the tension stronger or is the weight stronger? And the sum of the forces in the y would be tension minus weight 2. Alright. So, let's look at these questions that were asked now that we've done all the preliminary work. It said, what must mass 2 be in order to achieve a constant velocity? Or, in other words, in order for the system to be in equilibrium. Well, we know that if it's in equilibrium, the two tensions must equal each other, right? The tension pulling up on the box 1 and pulling up on box 2. So, if we set T equal to T, the first tension for box 1 is obtained from over here, and we know that that is going to be the x component of the weight. Right? And if we use trigonometry, we'll find that that's going to be mass times gravity, that's mass 1, times sine of 30. Squeeze that in there. Go back and look at the review on free body diagrams and forces if you don't understand that. Then for, that would be right here plugged in. And then the second tension coming from over here, we could solve, would be equal to W2. So W2, weight is always mass, this respective mass is the second mass times gravity. In this case, there's no angle, right, because it's straight down. Now, what can we do? We can cancel the gravities. They're common. And we know that that's 50 kilograms. And we know sine of 30 hopefully is 1/2. Remember that from your trig days. So mass 2, we just found out, has to be 25 kilograms. If it's 25 kilograms, then the system will move with a constant velocity and will be in equilibrium. Okay? We'll make it bright yellow for an answer. Now, let's see, what was the second question? The second question is, what is the tension? Well, the tension, we should realize, is nothing but W2, right? And if you plug into this formula here, you should also get the same answer. So, what is W2? Well, to find the tension, this is question B, this was question A over here. A little bit all over the place. Hopefully you can follow my logic. There is a method to this madness. So, I was trying to find the tension. No. Yes, the tension was equal to W2 is the easiest one. So, you take mass 2 times gravity, which would be 25 kilograms times 9.8 meters per second squared, and that gives you, let's see, where's my handy dandy calculator? Or actually I did calculate that, didn't I? It was 212. newtons, I believe. If you remember, a newton is a 1 kilogram per meter squared, or second squared. Alright, so that would be your tension. Technically I should have used, what, 2 sig figs there, so 210. I don't know if your class would use sig figs, so that would be a 0 right there if you do. And then the last question was, what is the normal force? So part C, I'll do over here. Part C, the normal force, if you remember looking up at this equation right there. Was the y component. That weight, so normal force would be pull mass 1 times gravity times, in this case, the y component would be cosine 30. That would equal 50 kilograms times 9.8 meters per second squared times cosine of 30, which is root 3 over 2. And when you do all that, you get the wonderful answer of, let's see, I wrote that down somewhere. Uh-oh. Sorry, guys. That was my 210. Whoa! Everything's falling apart. Let's undo that stroke there. So this one was the 210 newtons, and T2 apparently was something else. Let's find out what T2 was. I'm trying to find out my paper here. Did I not write it down? Alright, I'm just going to bust out the calculator and redo it. So it would be 25 times 9.8. 245 newtons. So if we were to use 2 sig figs on that one, so it'd be 245 newtons. With sig figs, we would have 2 there, so it'd be 240 newtons if we did sig figs. No sig figs, this is with sig figs. And then this one was 212 with no sig figs. And then, let's see, this one has one significant figure from the 50. So that would be 200 if you did sig figs. Alright, well, this is clarified in an example with no tension. There's plenty of more examples in your book that you can practice. The easiest way to overcome the fear that you might have when dealing with these problems is to do a bunch of them. That goes for anything in life. So make sure you just practice, and go back through. Look for keywords again, like constant velocity, right, or equilibrium. That's what your indication is for Newton's first law. I hope that has clarified any confusion that you might have, and make sure you check out the example that has friction as well.